We will now do our probability review part 3. So this is going to deal mainly with, let's see, binomial and geometric situation, but also two-way tables is another type of problem that exists in probability. So here's our formulas, page 2 of your formula sheet, and we've talked about these in regards to the general addition rule and the conditional probability, the mean and variance for a discrete random variable. Now we come upon these three things that we are going to use now. This, if it's binomial, we have a binomial situation, and there is our binomial probability calculation. There is our mean for our binomial random variable, and there's the standard deviation. And after that, we've got sample and distribution problems. So these three things are relevant to what we're fixing to do. So the first thing I want to talk about is how do you recognize a binomial problem? How do you know something is binomial? And so the first thing is, well, you can use the acronym BIN. It's binomial. First of all, it has to be binary. It's got to be a success-failure situation. And so what we'll have is we'll have some proportion. It'll say like P is something like 0.2. It'll say like 20% of the people in this town own a house, or 20% of the students in this school drive a car, or whatever. But it's got to be a success-failure. It can't be like political party, Republican, Democrat, other, three possibilities. No, it had to be like Republican or not Republican, that sort of thing. It has to be binary. And then we have to have independence. So independence sort of effectively means that this is the same for every trial. It's always 20%. All right, so if we're using sampling without replacement, we would have to have our population size be at least 10 times our sample size. But effectively, you look for the set P that does not change, and then N, so that's our I, and then N is number of trials. Number of trials is set. So there'll be a number of trials for this. So there'll be a probability, and then it'll say we took, it'll say, let's say 20% of, it is stated that 20% of people in a city own a house. We took a sample of, 20 of them, let's say. All right, and it will ask, well, what's the probability that, let's say, exactly 7 of them own a house? And so a binary problem, what I tend to look for is there's a probability, then there's a number of trials for that probability, and they're asked about a number of successes. And the probability never changes. Okay, it never changes. So anyway, so that is a binomial situation. And so here's an example of a context that deals with a binomial situation. So it says 11% of hyenas in a large national park have a particular type of tooth deformity. If you randomly select 10 hyenas, find the probability of that. Well, you notice we have a probability that if it doesn't change during the problem. And our fixed probability is 0.11. Then we have a fixed number of trials. Our N is equal to 10. And then in number 20 it says, what's the probability exactly 2 of them have the tooth disease? All right, and so that would be an X is equal to 2. And so our little formula that deals with this problem is this right there, and that we are going to use. And so what it's going to be 10 choose 2. We'll talk about that. And then we have 2 successes. So there's 11% probability success. We're saying success is having this tooth deformity. So that's happening twice. If we've had 2 successes in 10 trials, that means we had 8 failures. And the probability of failure is 1 minus that. So that's 0.89 to the 8th power. So what this formula is, it's saying what's the probability you'll have 2 out of 10 successes, or 2 successes, 8 failures. That's the probability of 2 successes. That's the probability of 8 failures. And this is the number of different ways they can be chosen, because it could be that the first 2 hyenas had the tooth deformity and the next 8 didn't. Or it could be the first and the third one had the deformity and the rest didn't. Or it could be the first and the fourth, etc. This is the number of different ways that can occur. So let me show you how to find this with your calculator. And so what we'll do is to find this function here, 10 choose 2, what we'll do is we'll go to the math button. And we go to math, we go to probability, and it's that. It's the combination 10 choose 2. So we hit enter, and we go 10, and then choose 2, and n in fact is equal to 45. So this is going to be 45 times 0.11 squared times 0.89 to the 8th. And so I'll just find what that is. So I will just say that number times 0.11 squared, and then times 0.89 to the power of 8. So that would be 0.2143, approximately 0.2143. Boom. Okay, so there we go. And now I'm going to show you a little shortcut with your calculator. You have to be able to do that, though. It's a frequent thing in multiple choice problems where they give you this problem and then the multiple choice looks like that. Of course, now the wrong answers will have something different from that, but the right answer would be that. So you have to be able to recognize that formula, to be able to get it off your formula sheet and recognize it. The other thing you could do is a binomial PDF. All right, and so binomial PDF is on your distribution menu. So if you go second distribution and you scroll all the way down, binomial PDF is for 1 point, and CDF is cumulative. So PDF, the number of trials is 10, the probability of success is 0.11, and your number of successes here is 2. And so you go like that. Now, in a lot of calculators, it'll immediately take you to that screen, and it goes alphabetically, N, P, and X, N, P, and X. So you'd write them like that, and you'd hit enter, and you get the same number. So showing your work, you could either show that, or you could write binomial PDF, but you have to label the parameters. You can't just write the numbers. So N is equal to 10, P is equal to 0.11, and X is equal to 2, and then, of course, show the answer there. And so there you go. That's a binomial PDF problem. Now, what's a probability that at least 3 of them will have the diffuse disease? So, and that leads us to talking about what is a binomial distribution. A distribution is every value a binomial random variable could take. So this is saying what's the probability that you're going to have at least 3 successes in 10 trials. Think about this. Let's say X be equal to our number of successes. We could have 0 successes. It could be that all 10 of them, in essence, don't have the disease. All right, or you could have 1 success, or 2, or 3, or 4, 5, 6, 7, 8, 9, and 10. All right, and so and if we found each of these probabilities like we did up in number 20 here, we found this value of probability 2 successes. That would be our binomial distribution in essence. Well, this is saying what's the probability that at least 3 of them, at least 3. So that would be 3 or more. So back in the old days, what we could do is we would have to use this formula to find all those values. But as you can imagine, maybe it would be easier just to find these probabilities and then say 1 minus that, because all these probabilities have to add up to 1. All right, and you could do that, and it's a bit tedious. It's not that bad, but we'll do what is known as binomial CDF. CDF is a cumulative function. Cumulative means the probability of a certain value or before it. It accumulates up to there. Okay, so and it always is working to a less than. So we'll do binomial CDF, and so we would realize, that the probability that X is greater than or equal to 3 is equal to just 1 minus the probability of that not happening, that it's less than or equal to 2. So like I said, binomial CDF always works with less than is the reason I'm doing this. So once we find the probability of 0, 1, 2, then we say 1 minus that, and we got it. And so that's just going to be 1 minus binomial CDF for cumulative. CDF, where our N is equal to 10, our P is equal to 0.11, and our X is less than or equal to 2. And so let's see what that is. And so we will go distribution, and we scroll down to binomial CDF. There it is. And so the number of trials is 10. Our probability of success is 0.11. And the number of successes is 2 or less, so we just enter 2 there. So we go like that, and so we get 0.91156. So that is equal to, and I'm going 1 minus that, so it is going to be 1 minus 0.91156, and that, in fact, is equal to 0.0884, approximately 0.0884. There we go. And so that's a binomial CDF problem. All right, so then we have this. If you randomly select 20, now our N is 20. It's our sample size. What are the mean, or the expected value, and standard deviation of the number of them with tooth deformity? Well, the mean, like we said on our formula sheet, is just N times P. Okay, and there's our standard deviation, the square root of N times P times 1 minus P. And if you think about this, hopefully this is logical. It says 11%, and so what are we expecting is 11% of them. So the mean is just going to be equal to x times p, and so, or it's going to be equal to n times p, in the sample size, n times p. And so that is just going to be 20 times 0.11, and that, in fact, is equal to 2.2. Don't round it. It's a mean. It's an average. Don't say, so therefore we're expecting 2. Leave it. We're expecting 2.2. This is if we were to look at a large number of samples of size 20. This is what we're expecting them to average. And then our standard deviation off of that formula sheet is n times p, so it's 20 times 0.11 times 1 minus p, which would be 0.89. And when you do that, you get about 1.39938. So that is the average amount that it would vary from the middle in repeated samplings. And so those are the binomial problems. And so then we have a geometric. If you were to randomly select hyenas, what's the probability that the first one you select that has the tooth deformity, the first success? And whenever it asks, when is your first success, it's talking about that. All right. That's a geometric situation. So it's a situation where you just need one thing. For whatever reason, somebody needs just one hyena that's like this. They don't need like 2 successes out of 10 or whatever. They just need one success. Maybe, or in another context, it could be they're going to find someone to do a job. And so what's the probability that their first success is going to happen by a period of time? But so when its first success is geometric, and you could use geometric PDF and CDF on your calculator. I just like just doing this intuitively and saying, what's the probability of first success is on the 9th one? Well, if your first success on the 9th one, what that means is your first 8 trials were failures. And then you had 1 success. That would mean your first success was on the 9th trial. What's the probability of 8 failures? Where if our probability of success is 0.11, our probability of failure is 0.89. And the probability that it's going to happen 8 times is that. We can multiply it because the trials are independent. Okay? Times the probability of success is 0.11, and when we do that, we get 0.0433, like that. And so then it says this: if you randomly select hyenas, how many would you expect to look at before you encounter the first one with a tooth deformity? And so that is in essence the mean of a geometric random variable. It's always equal to 1 over p. And so that is equal to 1 over 0.11, and that's equal to 9.09 repeating. Don't round it. So we're expecting our first trial around the 9th or 10th one on average. It's not just with one attempt. It's if we did this many times, many times, on average, our first success would occur at 9.09 repeating. So you report it just like that. And so that is a quick run through of binomial and geometric. And then the last thing we're going to look at is a two-way table. Now, two-way table, a lot of people find these problems to be pretty intuitive. In other words, I think you really could figure out a lot of these things, I think, even without having AP Stats. But anyway, and so here we go. So a researcher takes a random sample of voting age people in a town and surveys them. He finds out their gender and their political party affiliation. So, in chapter 1, we were asked to graph this and comment on it. So we would make a side-by-side bar graph or maybe a segmented bar graph. And, of course, we would have to create percents out of these to find the conditional distribution, because we want to know the percent of males that are Republican, not the number. But anyway, so all that's in chapter 1. But right now, whenever you're given a two-way table like this, it's a good idea to make the marginal distributions. In other words, add these up. The total number of Republicans, 42 plus 38 is 80. The total number of Democrats, that plus that's 86. The total number of others is 38. And you add those up. The total number in our survey is 204. And then for our males, the total number of males, you add those up. That's 111. And then for females, you add those up, there's a total of 93. And now I can answer various questions in that regard. So if you were to randomly select someone from the table, find the probability they'd be a female Republican. All right, a female Republican, there's 38 of them. So it would just be 38 out of 204. And you can leave it like that. That's considered showing your work. You don't have to write the decimal. If you only wrote the decimal, there's a good chance it would be partially correct or possibly even incorrect. But make sure and write the fraction. That's considered showing your work. All right, then a female given Republican. Now, given, so this is distinctly different from the probability of female Republican. This is female given Republican. when it's a given problem, a conditional, you look only at what you're given, because that's all you're given. You can only look at what you're given. Given the Republicans, given it's one of these 80 people, what's the probability of female? Well, that's going to be 38 out of 80. So you only look at what you're given, and so that's 0.475. Okay, so there we go. And showing your work is showing the fraction. So there's a difference between female Republican and female given Republican. So a Democrat given their male. Well, given their male, you can only look at what you're given. We're just given this row, these 111 males. If you know it's a male, in other words, given it's a male, what's the probability of Democrat? Well, there's 57 of them. So it'll be 57 out of 111. So that's 0.5135. So there we go. Show whether or not they're independent. Now we have, and we talked about in previous videos, what does independence mean? There's two things you can show. All right, and I'll show both of them. So the first one is, you could say, what's showing that whether or not being a female and being a Republican or independent? Well, you could show this, is if they're independent, all right, if they're independent, this is going to be true. The probability of female given Republican is just going to be the probability of female. Because it doesn't matter whether they're Republican or not, the probability of female in this case would be the same. What's female given Republican? Female given Republican we found up here to be 0.475. Well, what's the probability that someone in this table is female? Well, there's a total of 93 out of 204. And so that, in fact, would become, so that is, let's see, I believe that's 0.4, so this 0.475 is not equal to, that in fact is equal to 0.45588. Those are not equal, so there's not independent. Okay, and so that's how you would, in essence, that's how in essence you would show that. Now, but it's really close, and you can certainly make the case that this difference is very plausible. It's due to sampling variability. But in the world of probability, we aren't really dealing, in essence, so much with the world of sampling like we were doing statistical inference here. In the world of probability, they're supposed to be exactly the same. But technically, I think you could debate independence here because it's really sort of unlikely. As a matter of fact, with 111 males and 93 females, it'd be really impossible that all the probabilities would be the same. The other thing you could do is if they're independent, the probability of female times the probability of Republican, it would equal the probability of female and Republican. And so if you did that, the probability of female, well, we just found that that's 93 out of 204. The probability of Republican, there's a total 80 of them out of 204. Is that equal to the probability of female and Republican, which is 38 out of 204? And those are different. Those are not equal to the same, so therefore they're not independent. And then lastly, our last probability problem, if you randomly select 3 people from the sample, what's the probability they're all males? And so this is a multiple event, so we multiply. You can multiply events either when they're independent, like this equation, or if you take into account their conditional nature. So what's the probability they're all males? Well, the probability the first one's a male, the probability that's 111 out of 204. So that's the probability that the first one's male. Given the first one's male, the probability the second one's going to be male, there's only now 110 males left because you took one out, and there's only 203 total people because you took one out. So then, given the first two are male, what's the probability the third one's a male? Well, there's only 109 males left over 202, and so you multiply them, and so that would be equal to 0.159098 approximately. Okay, now if you were using replacement like we've talked about before, and you would just take one person out, see whether they were male and put them back in, and then take another person out, it would stay as it would be the probability of male happening 3 times. So that is with replacement. If it had said that, in other words, you would have independence here. Here you don't. Okay, and so that is in fact equal to 0.161094. Pretty darn close, but you always assume that it's not replacement in a situation like this unless it says so. Okay, thanks very much for watching. That's the last of the probability videos, and I wish you the best of luck in working probability problems.